deterministic. I completely disagree with that. That's not true. Biology is all about holism. Physics is all about reductionism. I don't agree with that either. Biology has few laws. Physics has universal laws. Physics actually also have few laws. You can put all the laws of physics on a T-shirt. It's just difficult to solve them for any situation that you know. Schrodinger's equation, Maxwell's equation, and Newton's laws. And if you want to put Einstein's general relativity, then special relativity is pretty much that. The rest can all be derived from there, more or less. Complex and simple, yeah, I kind of agree with that too. So here's population versus essentialism. Essentialism means that each time I look at something, a certain entity, it's the same thing. So if I look at an electron, and I look at another electron, it's the same electron. I mean, it's no difference. Every electron is the same. They all have the same charge, same mass. They behave the same under certain situations. So physicists tend to categorize things into electrons, protons, carbon, nitrogen, In biology, and that was really a big problem with people that they didn't manage to understand evolution, is that every, what's a dog, right? These are all dogs, right? They don't look like, this is not, if our electrons would look this different, we would call it different names, right? We would all call them a dog. So there's this huge population, there's a range of, in each, a dog can be very many different things, a horse can be many different things. And that kind of helps you understanding evolution because, creationists, they think, oh, everything is just like in physics. You got a dog, a horse, and if you have a human and a monkey, and if a monkey changes into a human, how suddenly the monkey stops being a monkey and the human starts being a human or something like that. You don't have that problem if you think of everything having like a distribution, and if you go through a long period of time, you always have a certain edge of that distribution, which is going to be maybe a bit more human-like if you want on some aspects. But every trait, every genetic difference has this distribution, and the distributions are all different, so it's a much completely different thinking. The other thing that actually this essentialism thinking in biology also leads in some sense to racism, because people want to categorize. They want to say humans, biology, as far as I understand, race history don't make much sense. Because in different genetic traits we're all similar and different, and we're more different anyway than any other animal there is, and so they're really, maybe culturally it makes difference, I don't know, but biologically I don't think it makes sense. So I agree with that difference, I think, to some extent. Complex versus simple. Physics, that's really what we do. We're trying to make things simple. So, we want to find these laws. This is time-dependent Schrodinger equation, quantum mechanics. We can solve a lot of stuff with this. If you can't solve it, it's just too complicated to solve, but the law still applies. This is biology. This is some kind of signaling pathways I got this off Google, right? So don't make me explain it. Some signaling pathways in the cell. These are like some evolutionary trees of something. Where the evolution, the Tiere, so it's the evolution of animals. It's complicated, right? It's very complex, and this whole charge about stamp collecting is really unfair, because to figure out what's happening, first you have to identify all these different things, and you have to make lists of them, and then you can start to categorize and see how they all interdepend and what happens to them. So you have to. In physics, there's not much stamp collecting to do. I mean, there isn't that much to collect, I guess. Here's the holism in physics and chemistry. I disagree with, in physics we have some idea about holism, in the sense that you can start with a very basic laws, and then you take a law like this, and you see how it plays out, and it can make some very complicated structures. These are orbitals in a hydrogen atom. You can use that a little bit further, and you get molecules, and you can put some understanding about these molecules together, and you can come up with some very complicated molecules, like this protein over here. So you can work your way up from very reductionist kind of ideas to more and more complex ideas, and at each level we discover new phenomena. And physicists have a good understanding of that. We don't use quarks to understand the protein. We're not that stupid, really. I understand. Sometimes you read these things that some philosophers write about this. Certain philosophers. I don't want to say all philosophers would do that. But and you're like, no, we're not really not that stupid that we think that we can explain, human mind with quarks or something. That's just not. We know where the connections go. They go step by step. They don't go from here directly to there. That's actually really difficult. To solve the Schrodinger equation for a protein, forget it. It cannot. But we can go from here to here, from here to here, from here to here. Right? We can do that. Chance and contingency. I don't think it's unique to biology. Okay, yeah, you have this thing, platypus, pretty strange animal, looks like, a bill, and it has used electric fields to sense its environment, and it's poisonous and all this other strange stuff. You still look at dinosaurs again. If it weren't for this famous meteorite impact, this is all chance, right? We may be walking dinosaurs if this wouldn't have happened, right? We all have scales, standing here, who knows? But the same thing happens throughout the universe. The distribution of galaxies, that's all kind of by chance. The overall structure, there's a certain structure which has physics in it, but why is this galaxy here and not over there? It's just chance. Planets, this is our solar system, this is another solar system that people have identified. It's completely different. The fact that we're living on this planet that looks like this, it's all just chance. You don't have to go to biology for that. So this is just part of the universe. The universe is always part of chance and necessity. Those two things just, are the two things that are important. So chance is in physics, chance is in biology, necessity is in physics, and necessity is in biology. And those things together are what creates the complexity of our world, in my opinion. So there's no problem there. Okay, I want to talk a little bit about, again, technical, hopefully not too much, but you don't have to solve any of these equations. I actually did this for my students. But the point is that in physics we actually have one nice theory. That's maybe the only theory where we can actually go from a very low-level laws and see how new laws emerge. And that's called statistical mechanics. And it can be applied to some parts of biology too. Here's an example. You put some dots in a box, and you say the number of boxes here is the volume, and the number of dots are the atoms, right? And then you just say, like, well, how many ways can I distribute these dots in a box? And that's given here. Then you use a few other laws, the entropy, and you define some kind of tendency to increase the entropy and letting the dots distribute themselves more evenly. And this is all you need. And you come up with an emergent law, which is the ideal gas law. It's really amazing, because ideal gas law, this P is of course pressure, but there's no pressure here. It's just dots in the box. So a lot of laws emerge out of simple mathematics when you do the statistics, and so that's something which I think can be applied to some molecular biology for sure. It can really picture something. So here's an example. Famous experiment is people use an RNA, which is one of the carriers of information in your cells. It has a loop, and they apply forces to it, and they can see how this thing opens and closes. The loop opens and closes randomly, just closed, open, closed, open, closed, open, back and forth. And then you do the statistics, and there are certain laws in there, And so you can discover these things. You can even discover, here's a statement from earlier, movements unless directed are random, like Brownian motion. Something has to give direction to this movement. Well, we actually now understand from physics how you give directions to random motions in your cells. We understand pretty well, there's still open questions, how proteins, so-called motor proteins, the ones that you use to lift your arm, that are in your muscles, for example, which are called myosin, or this kinesin, which is the little walking proteins in your cells that move cargo around, how they work. And we have a basic idea how it works. We call it a thermal ratchet. You can have a Brownian motion here, but you rectify the motion, and it needs an input of external energy. We have a pretty good idea how this works. So this is one of the biggest problems this is Aristotle's problem, right? He was complaining about Democritus and saying, like, how can random motion of atoms, how can it explain all these directed motions that you see in animals? And on a very fundamental level, we have some understanding of that from doing this kind of reductionist stuff.